Good morning all. So Wes has kind of said what I've kind of come in here to talk a little bit about, because 10 years ago, actually at this QCon, was the first time I talked publicly about LMAX and the disruptor. So Dave Farley and I gave our first talk. We were both really nervous. 10 years later, I'm still really nervous doing talks. So if anybody ever thinks speakers get it easy, it's not. Not for me anyway. I find this quite nerve-wracking most of the time. Like, we had this attention grabbing headline at that time where we said we could do 100,000 transactions a second at under 1 millisecond of latency. And that was pretty cool at that time. Most systems didn't do that, if you've seen that. Some financial exchanges were in that space, so there's a very few applications that sort of were running at that sort of speed. And we're not just talking about the core of the system, we're talking about external requests coming in through gateways, processing it, sort of making this thing reliable and responding back to customers in under a millisecond. And we were just round about that. Sometimes we were a bit worse, sometimes we were a bit better. So on average, we were kind of around there at that time. 10 years later, is it 10 times better? Kind of interesting. Like, are we now running at 1 million transactions per second in the financial exchange space? Like, I'm not at LMAX anymore, so I'm not talking about that, but just generally in the exchange space, well, some of the better ones are at that level of performance. So we have gone up an order of magnitude in throughput. What about latency? Have we come down from 1 millisecond? Well, yes, actually a lot. So you sort of say, are we down below 100 microseconds? The best exchanges around are well below 100 microseconds, down to a few tens of microseconds typically. I can't say exactly what sort of speeds some have, but they're very low. But there's been a lot of really interesting changes over this time. And that's what I want to kind of talk about today and go through that. So 4 main topics. Looking at how things have evolved, particularly how design has evolved. How do we make things resilient, fault tolerant, sort of robust in this sort of space? That's also really important, and there's been some fundamental changes there. Performance, as I alluded to, has stepped forward significantly. I'm going to get into that. And how we deploy these things has also quite significantly changed in the last 10 years. And these are all kind of wrapped up together. They're not really distinct. They all interact with each other. There's some interesting ways they play together. So let's start off first of all with design. And if you look at an exchange, they're all designed in a similar sort of way. Typically, they're state machines. So you apply a set of inputs to a given state that will bring it to a new state. This is pretty old computer science, been around quite a while. And if you're looking at the types of state machines, there's many and more. Most are typically melee state machines, where we're applying inputs to state to give outputs, or inputs to state, and we get a new state. And that's how things tend to work. Pretty simple. Most people don't build applications thinking like this, but most of our programs are state machines, whether you like it or not. They're probably just not particularly well-defined state machines and how they work. These sorts of systems need to be much more strict about that. And particularly, we want to look at replicated state machines, because we want something to be reliable. It needs to be on more than one node so we can tolerate failure. And from there, we can then recover and go forward without losing customer data and state and things like that. So to do that, we've got to order our inputs. So every state machine must get the same ordered set of inputs to come to the same result. The execution of those orders within that, so as the events change the state, that change must be deterministic. And there's some quite surprising things in there. Like, do most people here know that if you program with a hash map in Java, that if you iterate over it, it's not deterministic? So you get surprises in some of these things, and lots of data structures are quite surprising that they're not deterministic. So we need to make sure all our state is deterministic, and we need to be able to deal with that. And if we have got that, we end up with this same state and the same set of outputs across a number of replicated state machines. That gives us our reliability, our ability to tolerate failures at the end of this. We end up building a distributed log. So most people will take a log of the inputs, deal with that, and replicate it, and then we can get the state machines to the same point. And that's the bit that's formally studied and well understood. There are ways it's played with. You probably have heard of event sourcing, where it's kind of a little bit mushier, where it's not as formally studied, and we'll be looking at changes and replicating the changes. Now, databases tend to do a similar approach to that, but they do that much more formally. So I get to see many event sourcing systems that kind of fail because people don't follow the right rigor and do it formally enough to make it work. So I want to talk about replicated state machines as formally understood, and those ones can get us to nice, reliable systems. The cool thing with this is once you've got the ability to process these events in a nice deterministic way, we're not dealing with databases, we're not dealing with all of this sort of horrible stuff like ORMs and things. So we can have these really nice, rich domain models, which is actually a great thing in finance. It's one of the cool things you get to work on. Things like matching engines, risk systems, surveillance systems, all these, they're very rich, interesting domain problems to work on, and we can work on them with quite pure, very elegant models. So it's a kind of fun space to work in as well. And within these domain models, we've got lots of relationships between our objects. And for this, we've got to represent these relationships with something, and that's where data structures come in. So you get to do like quite a lot of cool computer science, either picking data structures and choosing the right ones, or even designing data structures from scratch. Like to make the best matching engines that are out there, there are not off-the-shelf data structures to do this. You end up designing data structures specifically for this purpose, and it works really nice as a result. So if you work in that space, you get to do quite cool things. In fact, some of the best people in the world at working on matching engines, that's pretty much all they do, and they get to design these and work in a kind of cool space on this. And it is a computer science problem and a domain modeling problem. Within this space, this is something I've seen evolve over the last 10 years, particularly how we deal with time. Time's a really interesting problem in this space because the time needs to be consistent across all of the machines. And so you can't read the system clock. That's not something that ever happens here. It shouldn't ever happen. Sometimes it does, and things go wrong. So we have to catch that and deal with it in other interesting ways. So we usually are timestamping events as they come into the system, maybe even timestamping them at the hardware level by putting a timestamp onto a network packet, using very accurate clocks, disciplined to atomic clocks that are GPS synchronized. And so we can be very precise at that level, which is a kind of nice thing to do. But what about if I want to set a timer? So if I place an order into an exchange, and that order goes in, and 10 minutes later, if it's not matched, it must be cancelled. Or maybe even 10 seconds or even 10 milliseconds later, you may want to cancel it if it doesn't fill straight away. We have to set a timer for that and wait for the timeout to occur. Now, if it fills in the meantime, you're not going to fire that timer. You want to cancel that timer. But if it doesn't fill, you want to have that timer go off and deal with that. Now, if you've got a replicated state machine, what do you do here? Well, a typical approach is to pulse in timestamps. And you see that a certain amount of time has gone past, and then you're reading that, you're looking up and go, okay, have any timers that need to expire? Got a really interesting computer science problem there. How do you manage a lot of timers and deal with it efficiently? Things like timer wheels and priority heaps, and there's all sorts of cool data structures for dealing with that. Well studied in the operating system space, so you can draw from there. But these events going in end up in your log. You end up with a lot of events in the log if you want very high resolution on your time. So let's say you want to have microsecond timestamps, you will end up with having 1 million events per second in your log, just dealing with the time. So you need to deal with that in some interesting ways too. And there's ways of doing that. It's actually better if the infrastructure is built to cope with that problem. And having seen people go through the different ways of doing that, it's now pretty much acknowledged that you need to do that in the infrastructure to do it well. And there's solutions to do that. So kind of just being aware of some of this. There's also been a big evolution in fairness in this. Anybody who's worked in finance will know it's pretty much a rigged game. It's been rigged by the banks and large corporations for a long time. We now have got retail customers dealing, and we've got lots of new people coming into this market, and fairness is becoming something that people want to have, and it is changing. We're even seeing in markets where we'll get different market makers are playing off each other. They're not playing by rules. High frequency trading changed a lot of this, so we need to work out how to make it more fair, how to make it more transparent, and this has caused a big difference in the design of some of the exchanges. Here's one example here. 10 years ago, an exchange would have looked something like this. We have multiple gateways facing off to customers, and we probably had 2 matching engines at the back of that. Sort of one was there to take over from the other one if it failed, so we got that level of redundancy. Oh, for some reason my slides have gone. Let's try. Well, I don't have slides. If somebody can sort out a AV at some stage, that would be great. I'll talk a bit more in the meantime. So we've got these multiple gateways. People can connect to those gateways, and that starts to send orders into the system. Now, if you're a market maker and you want to get a competitive advantage, what you can do is you could connect to every single gateway that an exchange has. Simple technique to do. You can start measuring which is the most responsive gateway that's there, and then from that you can start putting your orders through the most responsive gateway. Kind of makes sense? That's a pretty fair technique. You could do that and that'll work, and we're kind of fine with that. What if you want to be a bit more unpleasant? So you're not just wanting to compete, you want to compete, but you don't mind putting other people down. How about you work out which is the best exchange, or which is the best gateway to connect to? You connect to that gateway, and you can start sending your orders through that. But what about all these other gateways? Well, what if you start stuffing orders through those other gateways that you don't care for matching? Like, you put them at prices off the market, so they're not good prices, they're not going to be taken, but you stuff loads of traffic into them. They're now stuffed up with traffic, so other people can't compete. And then you go through the gateway that you've set up with knows fast, and you're going to send your orders through nice and quick. That's not fair. But that's what started to happen. A lot of that sort of stuff started to happen. So how do we change that? What if we only have one gateway? People can't do any sort of nasty things then. Everybody has to go through the same gateway. And this is where a number of exchanges are now moving to having a single gateway that you connect to. You connect to that single gateway, and everybody goes through it. Now this has got some interesting implications. We don't get the games playing, we don't get all of that extra traffic stuffing orders through them. That's actually quite nice. That steps down the load on the system quite significantly, but you've got a single point of entry for all traffic going through there. So it has to be really, really fast. So we're seeing this consolidation now in the gateways, the way we used to see consolidation in matching engines and risk systems, where everything went through the same point and we needed the traffic on there. We would go wide on gateways. We can't go wide on gateways anymore. So performance has started to really, really matter. And as a result, we can send the traffic through that, but we have to get it right. So we'll move to this sort of model where we have a single gateway will be connected to a matching engine. There's also something else that's going on, is we're realizing that the primary secondary means of fault tolerance is not sufficient, and I'll come back to that later. So we get multiple matching engines. How do we deal with loads of load, especially dealing with the internet? Well, we do have multiple gateways, but we're having gateways by classification of customer. It is perfectly acceptable under the regulation to treat an internet customer different from a co-located customer. They are a different classification of customer, and they can get a different level of service. But within a classification, they should all get the same equal fair service. So one gateway may be the internet, one gateway may be remote people, one gateway may be co-located people at the exchange. And so we can separate them out in various ways like that. So that gives us a little bit of an ability to scale, but we're still having to get all this traffic through, so we're having to focus on the performance of that. And one of the other ways we can scale up is we can scale up the matching engines and stuff themselves by sharding by, say, instrument or asset class or something where we don't have the relationship between that. Some markets are interesting where there's correlation between instruments, and we'll deal with liquidity across them because some things are fungible or can be fungible via calculation across that. So we get a little bit up, but sometimes it's actually easy just to shard by dealing with the instruments or different assets at that point in time. Like you may have indexes on one, you may have FX on another, you may have equities on another, you may have some of the biggest equities in a different exchange, and we deal with that separately. So we've kind of seen this evolving layout of the infrastructure. We're also seeing a move of asset classes to being exchange traded. We had a lot of over-the-counter trading. We have a lot of proprietary trading and broker-based trading in the past. More of it's moving to exchange, because on exchange, it's fairer, it's equal. There's better ways of dealing with that. So we're getting a lot more activity in this space, and an explosion over the last few years of cryptocurrencies and other crypto instruments that are being traded in this space as well. So lots of the new exchanges out there, this has started happening. And one of the things I actually like to see that started happening is we started trading energy now. I got to work with a company doing an energy trading exchange for Europe over the last few years, where renewables has become an interesting problem. So you've got wind, you've got solar, you've got all these. They're not predictable. So you may have one part of Europe's got a lot of wind, another part of Europe doesn't have a lot of wind. We need to move that energy around, we need to cooperate, and we need a means of trading that really fast on the fly. So this is sort of stuff that's starting to go on to exchange now as well. So really cool and interesting things happening here. So that's kind of where the design space is going. Where are we going for resilience? How do we make things fault tolerant particularly? So by fault tolerant, can we tolerate a fault and continue and go forward? 10 years ago, everybody in finance was doing primary secondary, where you've got a node that's your primary node, all your traffic's going through that, it's backing up to a secondary node. In the case of the primary failing, you can go to the secondary node to be able to continue processing. Not a very good approach when you actually look at it from the service you want to offer customers. A couple of things in that. If you've got two nodes and you get a failure, you can't automatically decide which one should become the new primary. So typically you end up with a failure at 2 o'clock in the morning, someone gets out of bed, tries to do something about this and screws it up because they haven't had their coffee yet. I know, I've been in these situations. You want the means to be able to automatically choose which node is the ideal node to be the primary connection and go forwards. But it's actually bigger than that. You start having a conversation with a lawyer around why do we have fault tolerance? So if I'm trading into a market, particularly if I'm allowing retail customers to trade into a market because they deserve more protections than professional traders, because they're not aware of the risks to the same level. So if I'm trading into the market as a retail customer and the primary dies and we go to the secondary, seems fair, we get to continue. You're now running on the secondary. What if the secondary fails? You now have no data. You have no way of reputing what has gone on. A lawyer is not comfortable with that situation. If you're going to go from primary to secondary, the only point you should go to secondary is to allow people to trade out of their position so they can go flat and be safe in the market. It is not a system that you can continue operating on except to clean out. Now, if you go with a different approach of, say, consensus, so let's start off the simple case of 3-node consensus. If you have one node that dies, you can continue trading because you still have another node beyond the primary. You've got a primary and a backup, so you're still trading safely at that point. You've also got a really nice case of you can work out which one should be the primary. So let's say we have a net split, and we've got split brain going on in a network with 3 nodes. They couldn't communicate to each other briefly, and then maybe 2 of them can and 1 of them can't. The 2 of them that can determine that they can form a viable cluster and continue. The single node on its own can't. If you have a system whereby you get primary and secondary and you get a net split, you cannot work out which one automatically become the leader. So we got algorithms that allow us to do this. And so we're seeing this move forward to doing this. Although what's interesting, in finance, I'm still seeing a large number of people doing primary, secondary, even though it's known to be a flawed solution. And we get loads of excuses, but we don't want to spend the money on the hardware. Hardware is so cheap these days. It's expensive in many financial organizations because the IT staff are shockingly bad and inefficient in how they run it. Like, I'm sure that you can hear the little giggle in the room here. Like, how many of us has asked for a test server and it's taking 4 or 6 months or 9 months to get it and stuff? That sort of level of service within an organization is going to die. It's the way of the dinosaur. There's much better solutions to this now. Now, when you look at these techniques to do consensus, it's been around for a long time. Like, 3 of the main proponents in this, Leslie Lamport, Barbara Liskov, and Ken Berman, did the majority of this work in the 1980s. Leslie Lamport wrote a seminal paper in '84 on time versus timeout for working with distributed systems that sort of spawned some thinking around this. Barbara Liskov being the first one to actually come out with a consensus algorithm after that. Paxos is a bit better known, but it came out later than that, and Ken Berman did a lot of work on virtual synchrony. So these were all sort of simultaneously coming out, and they give us the ability to have consensus and fault tolerance properly in a market. This was worked out in the 1980s. I find it shocking today that stuff that we know and we do it really, really well, we're still not using it properly in 2020. Like, people running primary, secondary in 2020, we really are a dinosaur. You need to wake up and find out there's better ways of doing some of this stuff. But what was interesting was all those approaches were hard. They're really difficult to understand, which is probably one of the reasons why they hadn't taken off. Paxos, probably the best known, but infamously difficult to implement and get right. Then the RAF paper came out in 2013, 2014, and this changed how people thought about this. And it's because there's an interesting goal with RAF. The goal was to build a consensus algorithm that was easy to understand, not to build one that was perfect or trying to deal with all of these extra edge conditions. The primary goal was to build one that was easy to understand. And this changed and revolutionized the space. Having implemented a bunch of these, it's actually not that much easier to implement than Paxos or some other stuff, but that's a separate thing. But a lot of the groundwork for this was actually Barbara Liskov's work in viewstamp replication. Raft is closest to that than some of what's gone before, but it has changed how we think about stuff. Cool thing is you get all these nice properties whenever you implement RAF correctly. You get election safety. At 2 o'clock in the morning, when you get a node failure and you get another one elected, you don't have to call the support people. It just deals with it. So I remember one of my customers was talking about how they'd come into work one morning and during the night they'd had a node failure and they just had an event in their console saying that it had happened, but another node was elected and they continued on and there was no drama to it. That's kind of nice. Yet that's often not the case whenever these things have gone. Like, I can remember situations back sort of 20, 30 years ago where in the middle of the night I'm tearing my hair out working with administrators trying to get the system to work again properly, and we're making mistakes because we're tired. We don't want to be in that sort of situation. So we've got this, things have got better as we've moved forward. How does some of this work? Well, we elect a node and that is designated the leader within it. So in this case, the middle one being the leader here. These are usually managed by, in RAF terminology, a thing called consensus module. So something manages the consensus within the cluster to work out where we can safely process any data to go forward. And we start dealing with a number of counters that are interested in this space. So this is a distributed system, and distributed systems, everything has a different view of what the state of the world is. Just like all of us in this room, we don't have a global shared memory. We all have our own local memory in our head, and we communicate with each other to reach some sort of consensus on a shared understanding. This is how these systems work. And so, how does this work out? So for some of these numbers, so the numbers here could be the number of bytes through the system, the number of messages through the system, whatever. We're dealing with a distributed log that's deterministic, so it's ordered, and we're going to send the same log to them all, but how far have we got through that log? That's the interesting question. Well, one of the things that's interesting, we just lost our slides again, and we're back, good stuff, is what is known in RAF terminology as the append position, is what have we appended to disk, append index or append position. So what if we safely got on disk in some stable storage so that if we have a crash, we can get that back again from the perspective of that node. So that's one of the things. So in this case, the middle one being the leader is at position 29, whereas the others are 22 and 23, because they could be lagging a little bit. They could have had a little pause, various things going on at different points in time. Typically, the leader will be ahead of the others because it is the one that's doing the sequencing, but that's not guaranteed. There's another index that matters, and that's what's known as the commit index, the commit position. And that is, what is the index the cluster has reached from the position, from the perspective of consensus? So what is the quorum of the cluster agreed to be it can safely recover from? Where quorum is defined as the number of items in the cluster divided by 2 plus 1. So quorum of 3 is 2. And if everybody says like, well, is quorum of 2 1? No, it's not. This is why when you go from a 3-node cluster to a 2-node cluster, you go in lockstep. You must go in lockstep to be reliable, because it's always n divided by 2 plus 1 gives you whatever the quorum is of something. So in this case, the consensus module has agreed that quorum is 25. Now, because it's got 29, the one over on the left has 25, and so it's determined it, but it hasn't maybe communicated it yet to the others that it is 25, so they're running behind. And this is the sort of problems we're dealing with all the time in distributed systems. They all have slightly latent views of where the world actually is, and so we have to deal with that. And then we've got, what have we processed? So the service is running on top of this infrastructure. How far has it got? And so there are various levels as well. Now, we cannot let the service go beyond the commit index, the commit position of the cluster. Otherwise, we can't tolerate a failure and recover our data. So we're not fault tolerant if we go beyond that point. So we need to gate all of these things to deal with it, because we could just lose a node at any given stage. And what's actually really interesting is, I'll talk a bit about in deployment, we're going to cloud a lot more often now. And in cloud, we lose nodes way more often than we used to lose them in our typical in-house infrastructure. So we're dealing with these sorts of cases. So we've lost the node. We need to elect a new leader. We'll tend to elect the leader that has got the most up-to-date view of the world under Raft. And so we've got a new leader, and we're talking to that from the perspective of our clients at that point. And we're replicating, to this case, the one on the right. Now, the one in the middle, if it was like it burst into flames and died and we don't see it again, that's fine. What's actually much more difficult is zombies. What if that took a big, huge GC pause and the others thought it's now dead? But then it comes back again and it's got a different view of the world and it still thinks it's the leader. We need to be able to deal with that cleanly and deal with it well and make sure everything resolves correctly, because whenever you look at split brain issues and failures, way more often than not, they're due to pauses, not absolute failures. And partial failures are much, much more difficult to deal with. And there's a lot of theory around how we deal with this properly. The core of it is that we got to use monotonic sequences and deal with it around that. So every leader gets a term in office and we need to track those. And so we know it's from a previous leadership term, not a one from the current. And so we will deal with this and move forward. So we've got lots of theory in this space. Some of this theory's been around since the 1980s, inspired by work even further back than that. I've implemented these sorts of systems many times and talked to other people who have done this many times. And what we've kind of learned is the model is important. Like, is it formally proven? Like Raft, Paxos, some of these other consensus algorithms have been formally proven. That's useful, it has value. More common than not, where these things fail is in how they're implemented. We all make mistakes. So what is our fidelity with that model? Have we programmed stuff up in code to actually meet the model correctly? And even though we think we have and we have good understanding, we all just make mistakes. And this is where one of the things that really gets to trip you up. And so if somebody says they can knock you up a consensus module in a few months, walk away from them. It's generally known in most operating systems that if you develop a new file system, it's 5 to 10 years before it's stable. Don't trust it for 5 to 10 years. I'd say with consensus systems, somewhere in the region of 3 to 5 years. So if somebody just puts something together, it's going to take that sort of time to reach the right level of model fidelity and code quality to where you can really trust it. Just because these are complex beasts and you got to shake the bugs out of them, even when the model is formally proven in the first place. So there's kind of lots of interesting things to think about here. So one way of getting resilience is the fault tolerance. Robustness is another thing that helps us. So we're talking about mean time between failures and mean time to failure. So how often are we going to fail? So robustness is about how robust is your code to inputs that are invalid? How robust is it to dealing with things that can go wrong? And we often don't give this enough sort of thought. So I kind of always like to ask this question of people is, how well does your application handle errors? There's some great studies out there that show that by far the most common cause of production outages in systems is unhandled errors and unhandled exceptions in people's code. There's loads of examples of where people have researched these and found that there's exception handlers with to-dos inside them. Please go fix this in production. And this really, really matters. So changing your programming style. Change your programming style so that if you've got an entry point to a system, validate all inputs before you do any mutation. Make that as good practice. This has been known, like Bertrand Meyer talked about this way back in the Eiffel days, about determining the preconditions, postconditions, and invariants before you start executing anything. So validate all of your arguments before you start to do any mutation on your objects. That way you'll end up with a much more robust system. And always, always check error returns on things and have a sensible strategy that you're going to apply when you deal with this. This will really increase the robustness of your system. Performance. That was kind of the highlight whenever we talked about some of these things 10 years ago. Got people interested in what was possible. So I'm going to come back to this, and it has changed. Things have moved on, and some quite cool stuff. One of the biggest things I think I've observed in the last 10 years is this awakening about the distribution of latency. We used to talk 10 years ago about averages. Some people still talk about averages today. Again, wake up call, you're one of the dinosaurs if you're talking about averages, because averages hide all sorts of evil. You've got to be looking at histograms and percentile distributions to see what's going on in your systems. Because averages are just so misleading. Like, throughput matters. It's kind of useful. Throughput, and what's your latency to given throughput as an average? It's interesting, but it's really interesting is what is the distribution on that? Because there's an awful lot of systemic and queuing events in systems that we got to think about. Now, systemic events, what am I talking about? GC pause, NUMA node, memory reclamation, a defragmentation on an SSD, various things happening, BAS locking revocation in Java. There's loads and loads and loads of examples of where something systemic can happen in your system, and that's it. You're just paused for a period of time, and this completely screws up your response times. And being aware of that. So be aware of these, be able to hunt them down, but able to track them. And it really helps. The other thing is like how you measure, and especially when you start measuring things like throughput over units of time that are not applicable. Like when you think about how many of us have all said, what is your throughput per second? Or what's your throughput per day, or something like that. That's a classic one. The big web companies talk about that all the time. What is the number of transactions per day they manage? You start doing the math on it, it's really not that interesting. Even per second, it's not that interesting. But if you look at real world systems, you're looking at what is it like in burst scenarios? What happens in that 10 microseconds when an interesting event happens in a financial market, or an interesting event happens like market open, market close, non-farm payroll release. These sorts of things is when within a number of microseconds a huge amount of traffic goes, and if you extrapolate it over a second, it becomes huge values. There is where throughput really matters, because you want to have incredibly high throughput to get through that burst really quickly so you're not queuing, because if you're queuing, you're waiting, you're not making progress. And usually the way you win for algorithms at that point is to be able to amortize. So if you can batch well, you can amortize your way through stuff. So you don't want to be having a linear relationship between input events and say IO events to disk, or network events, or anything that's going to be at a large expensive cost. You need to amortize into those to do really well. And it's a hugely interesting subject to go through that. Garbage collection is one of the systemic events. That was the big one that most people started to realize. You run on something like parallel old in Java or most of the various garbage collectors in C# and stuff, and you get these huge pauses. CMS was probably the better choice in finance for a long time, but it still had these full GCs that were nasty and stopped the world. So people went with one of two approaches, either a huge memory space, and you just hoped and prayed that you didn't get an event that was nasty before the end of the trading day, and at the end of the trading day you triggered a full GC and you kind of cope with it, or you just try to not allocate in your application. So those are the kind of major approaches people took. But then things started to change. People discovered things like C4, the Zul-Zing concurrently compacting collector, which was just revolutionary, where we could run at high allocation rates and not get really nasty GC pauses. Part of the history of that is that was originally designed for the Vega CPU, where you're looking at up to 1,000 CPU cores. So things like Amdahl's law was in your face all of the time. Stop the world events really got to hurt you. So they designed to cope with this and have a very responsive system. And so that's changed things a lot. And the nice thing is it's inspired other things going forward. So we've got like ZGC, Shenandoah. G1 I kind of just ignore in this space because it still is not really a proper concurrent collector in that sense. Like C4 leads the way. ZGC is very much inspired by it, but running way behind. It's not generational. It's got various other issues. Shenandoah is looking nice, especially on smaller heaps. So we're getting progress in this area. So it's kind of changing how we think about this. We don't have to do zero allocation like we did in the past. But when you really care about performance in this space, you start measuring cache misses more than anything else. So within your domain model, your business logic, your performance is almost directly correlated to the number of cache misses you experience. I get them like build these things all of the time, and you start to see what is your memory access patterns. Are you going to have the working sets fitting into your L3 cache to work really nicely as a working set? If you're going beyond that, are you going through memory linearly so the prefetchers are helping you? You have to work really friendly. Data-dependent loads are your enemy at this point. Otherwise, you don't get performance. The fastest matching engines out there are written in C because of the control you have over memory layout. This is one area where Java has really suffered compared to other languages. So things like C# has moved forward. Java is eventually starting to move this way, but it's not there yet and still has quite a way to go. So you don't see so much of the really high performance stuff in this space because it's purely about memory access. Unless people are putting stuff in big arrays or putting it off heap and dealing with it directly through unsafe, because that's the only choice that you have. And so we're sort of stuck in that space. So data structures is a fascinating subject in this space, and you get to see the cache misses. And you run profilers and you can see what's going on. You can see the traffic through your cache subsystem and to your main memory. And you can see how your instructions are playing out against the number of cache misses that you're getting. We've also started to get this nice move eventually towards binary codecs in this space. There still is a lot of fix, and fix is a horrible, horrible protocol that's mixed up at so many layers and so many levels. But so we're processing tag value stuff in ASCII. Eventually in finance, we've now started to move forward. So I was involved in SBE, and there's various other things that are out there like itch and mitch and ouch and seal and various other protocols that have all gone binary because it's so much more efficient than doing this in text. What's kind of interesting is outside of finance, the rest of the world is still living in la la land and doing JSON and XML and all sorts of horrible stuff. It's like just to burn the planet down and waste CPU energy and let's process everything. And it's just one of the things I want to rant about. I always keep hearing, it's human readable. It's not. Nobody can read UTF-8. I know a few people that can read ASCII, but nobody can read UTF-8. We have editors that allow us to do it. It's a tooling problem is what's going on there. And we need to move to have nice binary protocols. Like in the network space, it's a done deal. We know about it. We moved across. Even the old internet protocols, we're all moving towards binary protocols in this space. But yeah, we still have people obsessed with JSON. And now we've got the god-awful thing that is YAML that's gone everywhere too. Please stop this stuff. But yeah, binary is much, much better. We've also had the advent of Spectre Meltdown, all the speculation bugs, coming with the side channel attacks and various things. So things were getting, it was kind of interesting. 10 years ago, we were starting to see the free lunch bin over really starting to hit. So things really slowed down. Our CPUs were getting faster, but really at a very slow rate compared to what they were before. And then, but 2 years ago, so we had this really nice curve, and then it went like this, and then it went poof. And you've seen things got a lot slower as all the mitigation started to apply. I've seen huge costs increase when things got much, much slower. So actually a lot of the game now in this is working out which patches can you not apply, because then you get better performance. Like, do you know your system is safe from this type of vulnerability? So there's a whole really nice sort of world of consultancy where you can work out, okay, for this processor, I don't need this particular patch to be applied. Or actually, I know where I'm running it in this environment and what can talk to it. I'm not sharing anything else on hyperthreads and stuff, so I can deal with all of that as well. So it's a kind of weird and interesting world. But certain things have really increased in cost because of this. So things like system calls. When you make a network call or a disk call, things like that, it has got much more expensive. Stuff that's more subtle, like page faults, because there happen to be interrupts that are going into the kernel for dealing with this. You've got context switches associated with that, and it has a lot more cost. Like, I've seen people reading memory map files just get horrendously more expensive all of a sudden. These sorts of things, and also we're paging out our applications as part of the systemic problem. And then we're faulting them back in again. This all starts to become difficult. So we're having to look at M-locking memory and dealing with all sorts of interesting problems to get around this. So this whole cost space has gone up, and so we need to think differently. We particularly need to really amateurize. So again, if you're going to put a small amount of data in a network packet, it's incredibly wasteful. It was wasteful before, it's even more wasteful now. Same if you're going to go to disk. You want to fill that disk block. But we can get around some of this, making it better, by going to huge pages. So set up things like huge table FS, and you map your pages in there if you're dealing with memory map files, making sure your applications are all running properly and not watching out for some of the issues that come with NUMA and transparent huge pages. You actually want to make sure you've properly allocated huge pages and you've dealt with that correctly, and watch for the swapping issues that come around with that. Hardware has advanced quite a lot in this period, and in kind of really interesting ways. Disks, I think, are totally different than they were 10 years ago. We had really nice SAS spinning disks that could write sequentially nice and fast, and that's where these logs worked out quite well, but they're not good for random access. We get huge pauses, and especially when we're looking at our page faults that are going on, or we're swapping stuff out or anything like that, which you try to be avoiding. But if you did get this, you got huge pauses, because the spinning disk, you're dealing with milliseconds to go seek somewhere else on the disk. SSDs have changed this. They have really significantly dropped our latency. So we've gone from milliseconds down to tens of micros, or hundreds of micros in the sort of average cases, but the really good ones are now down to tens of micros. And then we've got things like Intel's Optane memory that came out, which didn't quite give us the throughput advantages we thought we were going to have, but has really helped with the low and predictable latency. Although we're still finding over and over again that if we access things in a random or arbitrary pattern, we have much more cost than we deal with it as a nice linear pattern. Main memory is very nice if we access it linearly, because it prefetches. Disks prefetch. We start dealing with how we write down and batch nicer. Disks feel less often if you deal with them in a sequential pattern than if you deal with them in a random pattern. So still having that understanding of what's going on under there. Networking's advanced hugely as well. I think the HFT and the whole thing that's been happening in the finance space has been wonderful for networks. We've got much lower, much more predictable latency now in our network stacks, and we're getting the benefit from that, especially as we've now gone much more distributed. So finance has been good at that. But CPUs have not got much faster. And that's what's kind of interesting. And if you actually look at the summary of what's happened in the last decade, is we've had minimal improvements in latency or response time from our hardware. Disks being the exception, but everything else is like memory, CPUs, latency is kind of the same. Throughput has massively changed. And this has flipped around how we got to think about design. We spent 4 decades of progress optimizing for latency, sort of optimizing to not use as much throughput and bandwidth and trade enough latency because that wasn't a problem. Now it's flipped. Bandwidth is abundant. Latency is not getting better because we've squeezed it to the end. And generation after generation, we're getting doubling or even orders of magnitude improvements in bandwidth. So we need to change how we're thinking around that. And part of that is our new APIs, particularly for I/O. Like the BSD sockets library has just run its course. It is not a good API for dealing with modern network cards. We need to go to much more asynchronous models, and so things like AFEI going to solar Flare cards, or Intel went forward with DPDK, and we're starting to see things like even the Linux kernel now, because of the system call overheads and getting the packet rates, IOU ring and ways of going, that is the only way to get to stress some of this hardware to what it's capable of. And it's similar on disks. We need to go asynchronous with these APIs, because that way we get around the system call overhead. You can only do so many system calls a second. When a system call is taking more than a microsecond, it means you're going to be doing less than 1 million of those per second, which means you can't do more of 1 million packets per second or I/O operations per second, yet the underlying hardware is capable of significantly more. So we need to deal with it asynchronously to do with that. And so we need to move forward that way. And so like, mechanical sympathy is more important now than it's ever been. As we're using abstractions, but if we don't understand what those abstractions are built upon and we use them correctly, we just are wasting cycles in this. Interesting question is, does programming language matter for a lot of this in the space? I've seen exchanges and trading systems built across all sorts of languages. The sort of Java, the C#, C, C++, a lot of Rust and all recently. This sort of thing is changing. I think it's actually not so much the language, but more the culture and the design around the language. And what do I mean about that? I love Java. I think Java is useful for many things, and the JVM is a great thing. But the design of some of its APIs are so hurtful to performance. They allocate too much. They have far too much data-dependent loads and not enough respect for memory layout. It starts to really hurt. C# is a bit different in some other ways. Like C# as a language and its control is better, but its VM and runtime is not as good as the Java one. We get to see this. The higher end of performance, it's going back a lot more to C, C++, and Rust, because we have so much more control. You can build the nice data structures, but it's not just that. It's getting access to these new APIs. Some of our managed languages are just so slow to even consider where our hardware is going. And so we're not getting to make any advantage of that, so we end up missing out. So what's happening is we tend to get much more polyglot style systems, where you'll develop some parts of systems in one language, some parts in another language, and actually, ideally, they can all work and interoperate very fast and efficiently, and that's the kind of ideal world. And we get to see that quite a lot more now, where things that aren't so high throughput, aren't so response time critical, will be done in other languages that maybe have a nicer environment and easier support and easier access to many more developers. So, deployment, kind of last section here. What's been changing here is it's kind of interesting space. Continuous delivery has had a huge impact. I think that was one of the things I was very proud that we were able to push forward at LMAX, and working with Dave Farley was a big advantage there. We just wanted to be able to turn things around fast, get that fast feedback cycles, and the secret to that is automation and actually looking at how you get feedback as quickly as possible. I still see people debating about, should they have a good test suite? Should they have the ability to do one-click deploy? All of these things, you still get some financial organizations that can only deploy every 6 months. It's just insane. You just don't get the feedback. You can't react to that. We need to have that ability to work that way and progress much more quickly, because the feedback cycles is what feeds innovation. If you can have an idea, test the idea, and find out if it's good in a very short space of time, including find out if it's bad, you don't get as wedded to it. One of the big dangers with anything that's got a long feedback cycle is things become our pet projects. We become wedded to an idea because it takes us so long to push it through a system, then we can't almost let the baby go. We want to see it succeed. It's much better if we can very quickly work out that something is not a viable idea and we can go a different route. And for that, we need to think about food. So people talk about agile. I really don't care whether you do stand-ups or not. That's all just cargo cultism. The key to agile is feedback cycles. It's all based on Little's law. Like, if anybody says they do agile and they don't understand queuing theory and Little's law, they're not doing agile. And that's about feedback. We have to have those fast feedback cycles to make good decisions and move ourselves forward and sort of think about how we can continuously deliver. We're seeing a lot more of a move to 24/7 operations, where we get new exchanges now that are going right around the clock. It was typical before that we would shut down at the end of the day and we didn't need to carry state forward. This has made it very different from how do we keep the state. We end up doing stuff like having to have snapshots of our state and recover from that. This also allows us to do rolling upgrades in live systems. And this is where like clustering and consensus is a better approach. You can take one node out of a cluster, upgrade it, get it back into the cluster again, do another one, and you roll these things. It allows us to do the hot upgrade and still be responsive. And we're getting a lot more move from that. And especially as we go to retail. Retail expects to access their systems at any time. We're also dealing with things globally, so we're getting a lot of change in that space. And we need automation, we need good monitoring, we need lots of things in that space to be able to do that and do it well. And we also need to scale flexibly. Like, a test I have for any system being built today is, can you run it on your live production system and use the same deployment tools, the same setup to run the whole thing on your laptop and debug it? If you can't do that, you've failed, which has some interesting implications. Hardware load balancers, specialized hardware and stuff and all, it doesn't really have a place in some of this anymore because it restricts what we can do. We need to be able to deploy everything to a laptop, so we need to be able to take threads and run them on cores. We need to be able to collapse them down and schedule them well. We need to split things apart and maybe have them communicate via IPC. Because we get to see this where we're now going from machines that had 4 or 8 cores or whatever in a server 10 years ago to now having 100 cores, no problem on a server. What's the obvious implication of that? Stuff that used to take up a whole rack now just takes up one machine. So you want to move everything on the machine, make things much more efficient by talking via IPC at that point. And we're seeing that now with going to the cloud. I'm starting to see new exchanges being built and deployed in the cloud. And so you need to take advantage of the hardware that's there, take advantage of the new APIs and be able to work with that and go forward. So kind of wrapping up here, that's the last 10 years. What's the next 10 years going to hold? If I see any sort of current trend that's going on, I think a lot of the performance race and stuff is kind of over. It's all about refinements. It's about quality of execution now. It's how well does your system stand up to failures? How well can you observe it, deal with it, manage it in production, run it 24/7, and face off to customers? It seems to be service is where things are really going in the future, and you've got to be reactive to a market that's changing so fast. If you're in a cycle where it takes 6 months, 9 months to do something to find out, you're just going to lose to the competition. You need to be much, much more reactive. And on that, I'll thank you very much.